board. Hello, world of statistics-seeking people. So what's the point of confidence intervals? The point of a confidence interval is to make a prediction about something in a population. And I gave an example earlier about asthma. I was poking around the CDC website looking for some information other than COVID-19, because although it's dominating our lives on the moment, there are other things going on in the world. Asthma was popped into my head because my wife has asthma, and that's a lung condition, and COVID-19 kills your lungs, at least damages them severely in most cases. So I'm worried that somebody with asthma could be at more risk for permanent, lifelong problems with their lungs that are worse than they already had. According to the CDC, 1 in 3 people has asthma, and I looked up some data on that. So they just had this initial post that says, hey, 1 in 3 people, right? A post my mom would appreciate. But then I dug deeper into a couple of other articles, like how did they figure that out? Turns out they have a confidence interval that it's actually between 7.3% and 8.1% of people have asthma. Okay, so could I say, yeah, it's more like 10%? And the answer is, well, no, that 10% is not in the interval at all. So it would be inappropriate to say 10 unless there's a good reason to overestimate, unless overestimating has some benefit and doesn't have some bad side effect. So are there times we might estimate a number of below or above the confidence interval for safety? Sure, there could be. In this case, I don't see a benefit of overestimating or underestimating their estimate. They said it's about 7.7%, right? I could not find their sample size at first. I eventually did find it, and I still got to double check it, but I had to estimate it because I couldn't find it. We'll talk about how to estimate sample sizes for confidence intervals in a couple weeks. So based on that estimate, I was able to jump into StatKey and run a simulation on it, and I got the same numbers they did in StatKey. And then I got on to explain a couple of things from their article over here. So I highly recommend you read it. This is like the extra credit assignment. If you're not sure where to go to find something for the extra credit assignment, then feel free to post something in the questions on week 6. And if other people don't reply to you on that, then I will. But the CDC could be a place to look. All right, other things. In the beginning of the quarter, I asked you in the syllabus quiz, how much TV do you watch each day? And mostly people gave me pretty straightforward answers, like 2, 4, hour and a half, none. But every once in a while, somebody gave me an answer that was a little more complicated, and I had to think about what they meant and interpret it because they didn't give me just a number. Okay, and then sometimes I would get a number that I didn't know what to do with. Like somebody said 25. Well, that's a problem because this was hours per day and there's only 24 hours in a day. So what do I do with that number? So I had to scrub the data. I had to turn answers that weren't numbers into numbers, or I had to delete them from the spreadsheet. And so over here, I have the scrubbed data. If anybody wants a copy of this, I can make it public. At the moment, it's not, I don't think. Based on this sample, of the people that started this class in week 1, you all watched an average of 3.4. If we rounded that to 1 decimal, that's a little bit too many decimal places, don't you think? Let's go 2 decimal places, 3.37. So just on average, you all claim to watch an hour and a half, 3.5 hours of TV per day. That was based on 44 people. Here's a histogram of that data broken down by hour. I read a study, I think it was 2015 or 16, that says the average American watches 5 hours of video stuff per day. I was like, holy shit, how do they have time for that? I don't have time for that. Even if I like binge on a weekend, I still don't think I average 5 hours a day. So that made me wonder. So I started asking students, and I do this in pretty much every class I teach. I say, hey, in the syllabus quiz, give me some numbers. Now, granted, this is a convenient sample, so it could be very biased, but sometimes convenient samples work out to be representative. You never know. Based on this data, can I support the claim of 5 hours? Well, just the sample isn't enough to do that. I have to do more work. So I'm going to put this in the stat key and then talk about the reasonableness of that 5-hour claim if this was a good representative sample. So I'm going to copy that, bring it into stat key, and we are doing a mean confidence interval, and I just want to edit the data. So why am I doing this? Well, a couple of reasons. That study baffled me. 5 hours a day is a lot. And then my hope is students don't watch 5 hours a day, that they watch less. And then the main point of application 6 is to think about the reasonableness of claims people make. Because people make claims all the time, right? You hear it in the presidential candidate debates. You're going to hear it in presidential debates coming up between the current president and the Democratic nominee. In the news, people make claims about averages and percentages all the time. How accurate are their claims? Is it based on data? And if they're making a public claim, it better be based on data. All right, so I do have a header row. Always double check when you're putting that in and check it or not. We rarely have a first column identifier. All right, so again, what the hell is stat key doing? What stat key is going to do is going to take my sample here of 44 people. It's going to turn it into a deck of cards. On each card is the number of hours somebody watches. Then it's going to shuffle that deck and randomly draw, if I do one sample, 44 cards again. Now it does so with replacement. So what that means is it shuffles the deck, it looks at one card, it writes down the number, puts the card back in, shuffles, draws another card, looks at the number. It does that 44 times based on these cards. So I'm not going to get a number here that's not in the original sample. But this number right here of 7 hours could appear more than once. This 8 over here could appear more than twice, and as it does here. Okay. So this is a random reshuffling of the original 44. And I'm only plotting the mean over here. And I'm going to do that again. I got a slightly different sample where the mean is higher. If I do it again, I get a slightly different sample over here where the mean is higher yet. What I'm creating here is called a sampling distribution. And a sampling distribution is a distribution of a whole bunch of other samples, right? It's not a population distribution. It's not a sample distribution. This is the sample distribution. Here is another sample distribution. If I take hundreds and thousands of other samples, all of size 44, and I plot only the mean of each sample, that is a sampling distribution. And in order to make predictions, we need sampling distributions. They do not exist. Confidence intervals do not exist without a sampling distribution, which means is some either theoretical or experimental way to generate new samples based on an original sample. This is only valid if the original sample is a representative random sample. So although this isn't, I'm going to make believe it is anyway. All right, so notice here that most of the samples have means that are close to the original mean of 3.368. Here it says the mean of all of these means is 3.366, right? Pretty close. If I do then a two-tail, which is what we want for confidence interval, 95% confidence level, and what that means is of these 7,003 new samples I made, so I have 7,003 samples, each of size 44, I'm only plotting the average. StatKey then finds the middle 95% of those 7,000 and says, here's the lower end of that 95%, 2.7 hours. Here's the upper end of that 95%, 4.04 hours. So what this says, let's suppose my claim, and hello, Micah and Andrew, I don't remember if I get to say hello to you. Let's suppose that this was a representative study of all Americans, right? So I have 44 representative from all over the country. Make believe that's true for a minute. Then this says that the average amount of TV that Americans watch is somewhere between 2.75 hours and 4 hours. Okay? So if somebody else says, nah, I think the average is 5. Is 5 hours in this sample? 5 hours isn't even on my number line. Okay. So is 5 hours reasonable? A claim that the average amount of TV people watch is 5 hours. According to this, that is not a reasonable claim. Okay? Now, look at the sampling distribution. It only ranges between like 2 and maybe up to 5, but this average right here is 4.898, not quite 5 hours. That's very different. Look at the shape of this distribution. It's very different than my original distribution. Okay? A sampling distribution will usually not look like the original distribution. And here's my original. Oops, oh, there we go. Okay, so that's super important. This is the distribution of a sample. This is a distribution of thousands of other samples, only plotting the mean. This is a distribution where each thing here is an individual person. This is a distribution where each thing here is a sample of 44 people, that then it's their average. Okay, so with that in mind, is the 5 hours reasonable? The answer is no. Is it possible that the real mean is 5 hours? Well, just about anything is possible. So yeah, it's possible, but it's not likely based on this sample. And that's important to think about. Almost anything is possible, but there's a lot of things that are unlikely. What's more likely based on this sample is that the actual mean is somewhere between 3 and 4 hours, okay, but not 5 hours. How sure am I? I'm 95% sure. What does that mean? That means if I did a whole bunch of other studies, each of size 44, that about 95% of them would actually catch the real mean, whatever that is, and 5% would miss it, okay? They would be out in the tail here. Okay? So it's possible the real average is somewhere above 4. It's possible the real average is somewhere below 2.7. I don't know. What's the chance the mean is 5 or higher? Well, there's a 2.5% chance kind of that, or 2.5% of my samples had means higher than 4. So I would say there's less than 1% chance that the mean is 5 or higher. Right? That's just a rough guess. Can a sampling distribution tell me for sure what the probability is? The answer is no, it cannot, but it can help me estimate it. Is it dangerous to overestimate the mean hours of TV people watch? Well, if I assume it's 5, and I think that could be a problem related to someone's home life or work life, then saying it's 5 might lead me to intervene and help people watch less TV. That could be a good thing. If I underestimate it and say, nah, I think it's about 2 hours, then people actually watch more than that, and I say it's only 2 hours, then I'm not going to intervene and say, you guys should watch less TV, and here's why. Okay, so I think it could be dangerous to underestimate in this case, but I don't think it's dangerous to overestimate. Every situation is different. Sometimes it's more dangerous to overestimate. And we just got to kind of think about that and wonder about it. And it's always hard to think about. Okay, let's do another example. So the next example I want to look at, if you want to join with me and try it with me with the data, you can. I posted an announcement a few minutes before this session started. And that is an example similar to the application. So you would find this in your inbox, or if you go to our course homepage, scroll to the top and click on that, then you should find a link to some data here, and I'll explain this data. So let me open that in an incognito window. And when you open it, it should look like this, and this says NCOV incubation. So I read a few studies. Ooh, and I see a couple people are in there. We have an anonymous pumpkin and an anonymous snake. Welcome to my journey here. This data is fabricated. I made it up. Now, I made it up based on research. The problem is the research is very complicated, and I'll show it to you quick here, but we're not going to use the real data because it's way more complicated. In the announcement I made, I link out to some of the articles I found about COVID-19 incubation period, and I listed them in order of readability. So like my mom could handle reading the Pop Sci article on it, but then after that, it starts to get way too detailed, okay? So I would expect you guys to be able to read the Pop Sci. The Science Daily, I would expect you to get most of that, but then after that, it gets like way too deep into statistics. And they talk about some things that I'm not really that familiar with. I have a degree in mathematics, and half of my degree in mathematics was statistics. In the upper math levels of the world, mathematicians don't view themselves as statisticians, and statisticians consider themselves a whole different breed of people than mathematicians. So a lot of us think that stats and math are the same thing, but professionals do not agree on that. So I don't have a degree in statistics, but I took a lot of graduate courses in it anyway while I was playing around. And the data that, so these kind of in the order. So the study kind of starts, actually it doesn't quite start here, it starts in China. And then these people at Johns Hopkins collected data from the researchers in China. They put that together into a spreadsheet with a whole bunch of codes about stuff, and you can go read about those codes if you want, it's rather boring. And what they have for data is an exposure window and a symptomatic window. So this is the lower end of when they think a person was exposed. This is the upper end of dates when they think the person was exposed. This is the lower end of dates where they think that the person became symptomatic, and here's the upper thing. Now think about that. This is a hard thing to figure out. If I get COVID-19, I'm probably not gonna know who I got it from, but after some research, I might be able to guess, oh man, yeah, there was somebody, several people in Pendleton that had it, and they went to the same Safeway as I did on the same day, so maybe I got it at Safeway, right? But I could have got it somewhere else, right? My kid maybe interacted with some other kid who interacted with some other kid, and kids don't tend to be symptomatic with COVID-19, so they won't know they're spreading it. So identifying when a person was exposed is very difficult. Second, when does a person become symptomatic? Well, you have COVID-19 and you can be giving it to other people before you're symptomatic. And then how do you know when you're symptomatic? When you have a fever? Well, if your fever develops, that means you've probably had it for a while. It's been incubating. By a while, that could be hours or days. And but you could have had other symptoms that you really didn't notice, like just a slight cough that you thought it was you swallowed wrong, right? Or it's allergies, right? I don't know. There's all kinds of symptoms people feel first. Could be digestive, it could be a slight cough, it could be a fever, but usually the fever doesn't come first. So identifying when exactly they became symptomatic is like nobody really knows for sure. So all these guesses have to be made based on medical records. And so they have a whole bunch of medical records that they sifted through, and they tried to estimate when they thought the person was exposed and when they thought the person was symptomatic. And then the difference of those two, once they figure those out, is an estimate of the incubation period. And it takes a ton of work to go from all of these dates and times here to end up with an estimate of the incubation period per person. So I kind of fudged it quite a bit based on what I read about their study, and I made up some times that I think fit that data kind of sort of similar. Now I only have 100 there, they had 181. So my data is slightly different. So what I'm gonna do is I'm gonna take this data and stick it in StatKey. Now my data does have similar parameters or statistics to theirs. They claimed their group of people had an average of 5.5 hours, and their standard deviation was approximately 2.3 hours. My min and my max don't quite match theirs, and my median doesn't match theirs, but I was just aiming at the mean and standard deviation match. Getting all the others to match means I have their data pretty much exactly, and that was not possible in the short time I had to play with it. And they had a team of people working on this for a month. All right, so Control Enter. So I just want to copy this data and stick it in StatKey. Control C, and then we'll see what we got from there. StatKey. Let's see, I'm doing a mean, not a proportion. And then I just want to edit and drop in my data. Oops, shit, wrong button. Try that again. I want this one. Control C, Control V. Okay, so just to check a couple of things. Is there a header at the top? Answer is yes, but I don't have identifiers in another column. So I think I'm ready. And I should get n equals 100 if I put it in there right. Okay. So when you plug in data in the StatKey, double check you did those check boxes right, double check you have the right sample size. So this is the original sample in a dot plot, which is kind of like a histogram. It is a histogram. And what I want to do is generate other samples based on this 100, and that's a sampling distribution. And they did use a sampling distribution, but they did a different kind than ours. We're doing what are called like normal-ish bootstraps distributions. They did a technique with a log normal distribution, which is beyond the scope of this course, but that's okay. In one of their reports, they explain why they used a log normal, but that's not important to us. How many do I have? 6,000, and you want at least 6,000. Now again, what does that 6,000 mean? I just jumped it to 7,000. It means the computer took this sample of this is one sample of 100 people, and it made 7,000 samples, each of 1,000 people, based on this sample. Okay, so all of the numbers here were used to create new samples, and each of those samples is going to be slightly different. And as you notice the bootstrap sample down here, as you point around through the table, it shows all the other samples, what they look like. In this bootstrap dot plot right here, all we're looking at is the average of each of those 7,000 samples, and each of those 7,000 samples had 100 people in it. The mean of the sampling distribution is usually going to be pretty darn close to the mean of the original sample. Notice that the mean of the original sample is 5.439, and the mean of the sampling distribution, that means all of these 7,000 means added up and divided by 7,000 still comes out to be 5.439. The spread, noticed, is much narrower, and that's because we're looking at the averages, and when you average, you eliminate the extreme values, right? The lower numbers and the higher numbers, and you're only focusing on the center number. So whenever you do just look at a graph of averages, it's always going to be narrower than the original set of data because you've averaged out the upper and lower values in your data set. So we want to generate some kind of confidence interval, and when you do your application, you only have like, I don't know, 10 to 14 people. You have a very small data set, and sometimes you can only have a small data set, and I'll mention that later. You may have maybe ask for a 95% confidence interval. You may be asked for a 99% confidence interval. In the study on COVID-19 incubation time, they used a 95% confidence interval. We'll switch back to that. If you make your confidence level higher, so again, what does the confidence level mean in terms of a sample distribution? Sampling distribution, better known as a distribution of sample means in this case. It means they're trying to find the middle 95% of these 7,000 samples and then identify which was the lowest mean in that middle 95% and which was the highest mean in that middle 95%. So StatKey says, according to my resampling of this data, 4.99 was the low, and 5.9 was the high in this 95% middle. Some of those 7,000 samples had a higher mean, like there's one way out here, I got a mean of 6.32. So this sample of 100 people had an average incubation time of 6.3 hours. And way down here, I have an average of 4.7-ish hours. So all different kinds of things can happen. So if somebody came to me and said, we believe the average incubation period is 4 hours. Is that reasonable based on the data that I have? The answer is no, that's not reasonable because 4 is off my chart. Okay? So according to this sampling distribution, what's the chance that a group of 500 people with COVID-19 had an average of less than 5 hours for the incubation time? That's about a 2.5% chance. What's the probability? I can't give you an exact probability. I can just estimate looking at this graph. What's the probability they had a mean of less than 4.75%? At 100 people on average incubation time. I would estimate that to be less than 1% chance of that happening. Okay, and again, I'm talking about not an individual person, but the average of a group of 100 people. Somebody says, hey, no, I think the average is 6 hours. Is that reasonable? It's not in my 95% confidence interval, but it might be in a 99% confidence interval. Yep, 6 hours is in a 99% confidence interval, so yeah, it's reasonable. Is it possible? Yes, it's possible. Is it likely? I don't know about likely. If getting an average of 6.05 hours, only about 0.5% of other samples of size 100 had a mean of over 6.05 hours. So a mean of 6 hours, that's probably more like maybe 1% of samples might end up with a mean of higher than 6. So it's not likely, but it's possible based on this information. All right, so let's write on this a little bit and talk some more. I'm going to go back to my 95, and I'm going to draw on this in my notebook because I want you to do a drawing for this. Let's see. Oh, I forgot to start my notebook. Word. Okay, let me see. I put my data, but I don't have the dot plot. Okay, Charlotte, sorry I missed your message. I tried to tell Zoom to ding dong me when somebody writes a chat. So let's see. The steps I went through to get Stacky to do this was to get the data, and I want to be careful in this case to not highlight the whole column, but to start at the top and just copy down to the bottom and not go any farther, and then Control C to copy, and then I go in, let's go and do a new Stacky window. This is a mean confidence interval. Edit data, first delete their stuff. So if it didn't get pasted in right, Stacky should give an error. Like if I tried to do this, it's gonna say something's wrong. But if it does go in, you should get a dot plot. So last thing I have is the 5.5. First thing I have is the title. That is a header row, that should be okay. And then you get a plot over here immediately. You're not gonna see the sampling histogram until you start generating samples. So you gotta hit generate sample and generate thousands of them. And you want at least 6,000. Okay. So this is a bootstrap dot plot, and I'm gonna write down what it means in my notebook. So let's see, I need this screen, copy, and I'm gonna draw my own personal version of this too, which is what I expect you to do for this. Add to new page, add to current page, here we go. All right, so what am I looking at here? Okay. So this is a distribution sample means for COVID-19 incubation period. Incubation, there we go, period. So the amount of time it takes someone who is exposed to end up being symptomatic is what the definition of the incubation period is. And according to this, the interval, right, so just a couple other things. So CL is confidence level. And let's suppose when I brought up my problem, I was asked to use a 95% confidence interval. You may be asked to do a 90 or a 99 or 98, depends on what version of the problem you got. Then I have a confidence interval. Usually we do a CI for that. So confidence abbreviate interval. And if I use interval notation, that would be saying it's about 4.99 up to 5.901. Another way I could state this is mu is a population mean, and it is between 4.99 and 5.901. So this is the confidence interval. Then we have the idea of a point estimate that's involved here. And a point estimate in this case is the population mean, and I'm approximating the population mean by using the sample mean, and my sample mean is about 5.439. The point estimate and the confidence interval are related through a margin of error. In this case, our book would call it the error bound on the proportion, and I have to calculate that. So to calculate that, I'm going to find the distance across here and cut it in half. So I want to know what is 5.901 minus 4.99 divided by 2. So I'm going to whip out a calculator for that. So parentheses 5.901 minus 4.99. Is that right? Divided by 2. Let's see if I got those numbers right. Looks right. Okay, so divided by, yeah, don't forget parentheses divided by 2, or do it in 2 stages. So I'm getting about, 0.5, 4.555. Let's add that. So I'm finding that the error bound is about 0.4555. So I need to interpret that. Let's see, has anyone else joined me that I haven't said hello to? Brett, welcome Brett, good to see you. This is being recorded, I will post it. All right, so let's see, I need to summarize this stuff, so let's see if I can do that. So I'm gonna need a new page to do that. I'm gonna redraw the picture by hand, and I'm hoping you will do this for me. So I asked in the application for a sketch of the sampling distribution. Okay, well, my sketch is gonna look a little different than theirs, but look pretty darn similar. I'm gonna have a horizontal axis for it, and I'm tired of writing in red. Let's write in blue. All right, so let's put that here, horizontal axis. And then I need to draw my best estimate of this curve here. And notice that's kind of a symmetric bell-shaped curve. We've seen it come up before. So I'm gonna draw my best version of that, but not so jagged. There's my best symmetric bell-shaped curve. Right in the middle of that is the mean, X bar, and that was 5.349. Am I getting that right? Good job. I am making in this case, a 95% confidence interval so that this region right here in the middle is 95%. And that leaves the tails to split 5%. So this tail here contains about 2.5% of the samples, and this tail over here contains the other 2.5% of the samples. 95% is kind of a standard. When I group 95% of these 7,000 samples in the middle, my particular distribution gave me 4.99 for the low on that, and 5.901 for the high. And then the rough distance from the center to the middle is what I call the margin of error. The book calls it the error bound on the mean. And I thought that was about 0.4555. Okay. So I'm hoping you'll make me a sketch like this. If you didn't, then message it to me, would be fine. You don't need to redo the whole thing. Just say, oh, oops, here's my better sketch. And then I need to interpret, what the hell does all this mean? Okay, so let's interpret. And the interpretation should be accurate, but my mom should kind of get it. So interpretation, and that's about as hard to spell as probability. All right, so usually in the interpretation, we state the confidence level. So you could state we, maybe you're working for a company, or you could state I. I estimate with 95% confidence that now I'm not going to say the incubation time, because it's really the average incubation time for everybody in the world is what I'm trying to estimate. So I estimate with 95% confidence that the average, you could use mean if you want, but my mom likes the word average better, that the average incubation, make sure you get whatever the variable is. What's the variable? The variable here is incubation time of COVID-19. All right, so make sure you define that so somebody else will get it. Incubation time of COVID-19 to be between 4.99 hours. And if you wanted to call that 5, I'd be all right with that, to 5.901 hours. Okay, so that's one possible interpretation of this. Another way to word it, sometimes we word it by stating the center and then add in the margin of error, and there's a bunch of ways to do that. How about with 95% confidence, the average incubation time Shit, days, not hours. Thank you for the correction. I mean, shoot, darn, jinkies. I almost did it again. Days. Days. Okay. Thank you. Do I have that messed up anywhere else? Nope. All right, welcome, Julia. 95% confidence, the average incubation time of COVID-19 is about 5.349 days. Thank you. And then I could stay within 0.4555 days or with a margin of error of 0.4555 days, but somehow I need to work in the margin of error in some language. So I'm going to just use the word margin of error with a margin of error of 0.4555 days. And, often I would probably, for a media thing, I might just say, it's about 0.5, close enough. In the press, they're not going to want so many decimals. Which one would my mom like better? I think my mom would probably like the blue one better. She's probably not going to like the term margin of error. She'll probably ask me a bunch of questions about what I mean by margin of error. But I think this would be better for her. So sort of the more common interpretation is that blue one right there. But sometimes it'll be stated like this right here. Okay, so that's the interpretation. Okay, so now let's play with a claim here. So some group claims the incubation time is 14 days. Okay, so let's look at that. Okay, so some group comes to me and says, hey, the incubation time is 14 days. Boom, done. Well, is that possible? Yes, that is possible, right? Anything's possible. Some people took, I think I remember seeing one study that there was they believed it was 21 days before somebody finally became symptomatic, that they actually noticed the symptoms. So yeah, 14 days is possible. Is it likely? Well, is 14 anywhere in my interval? 14, if that's 5 and that's about 6, 14 is way off the page. Okay, so 14 is unlikely. So I could respond to this and say, well, 14 days is possible. Almost anything is possible. Now, if they said the incubation time was -2 days, I'm like, -2 days makes no sense. That's crap, right? That would be impossible. This is a positive number of days. That's possible. So 14 days is possible, but it seems unlikely based on the data. So they might respond, oh, well, how unlikely do you think it is? Ooh, now that's a tough question I cannot answer, but I can guess. So if I look back at my stat key graph here, so, and I'm gonna go back to, let's do actually a 98% confidence interval just for fun, because with 98, that makes the tails split 2%. So each of the tails gets 1%. Okay, so 1% of the samples similar to mine had a mean incubation time of above 6. Okay, so I could say, well, the probability of having an incubation time of 6 days or higher is about 1%. 14 is way off this page. So it's way less than 1%. Do I know how much less? The answer is no, I don't. I don't have enough data to estimate that. So I could just come back and say, well, the chance of you finding another sample of 100 people with 14 days as the mean time for the 100, that's less than 1% chance of happening. It's less than 1/10 of 1%. It's probably less than 1,000th of 1%, right? It's way off the chart, unlikely. Okay, so estimate of likelihood. So using the probability notation we used before, the probability that the sample mean is at let's see, at is greater than or equal to 14. You can't do an equal to with these things. It's got to be greater than or equal to or less than or equal to. And this is a conditional probability, knowing that my sample actually has a mean of about 5.349, that probability is less than 1% for sure. So it's unlikely, right? All right, next thing. What should I recommend they do instead? Well, is there a problem with saying 14 days? Well, in the data that I had, the max was what? It's not the data. The fictitious data, the max was 11. In the study that Johns Hopkins did based on the it was kind of like a stratified random sample from China. The max, I believe, was 14 days. No, it was higher than that. I don't remember, but it was higher than that. So let's see, where was I going with this? Oh, what am I going to recommend? What's the pro and the con of overestimating the average incubation time? Well, if I say, hey, the average incubation time is 5.5 hours, so you should stay home alone for 6 days. Okay, all right. Is there a chance I'm wrong about the incubation period? The answer is yeah, there's a chance I'm wrong. There's a chance it's higher. So in this case, an overestimate's probably a good thing. So I'd say, well, you know, some people did show an incubation time of at least 11 days. So maybe you should stay home for 2 weeks just to be safe so that you don't infect somebody and kill them with COVID-19. So in this case, yeah, I think you could overestimate, but we should probably be honest with people and say, you know, the average time was 5.5 hours, although people did have up to 2 weeks before they showed symptoms. So the study does talk a little about why we might make a claim that you should self-isolate for 2 weeks just to be safe, to make sure you don't have the virus, or to show that you are symptomatic and then we need to intervene and do something about it. Would it be safe to underestimate? Would it be safe for them to say, well, when I look at this, I like 5 as an estimate better. 5 is a nice number, right? And a lot of people like nice numbers. They don't like fractions. They don't like decimals. So they might say, you know, the average incubation period it's 5 days. And again, the problem with underestimating in this case is that you're misleading people, and maybe they're thinking they're safe. They don't have it when actually they probably should wait longer. Okay. And again, this is an average of 100 people. If we looked at the histogram of the original data, so if I were to graph this, it's got a very different looking histogram than the sampling distribution. Google's thinking about it. Thinking about it. Not a line chart. That is totally meaningless. A dot plot would be equally meaningless here because this is not paired data, but a histogram is very meaningful. Yeah, so this is kind of symmetric. It's got a spike here where a whole bunch of people had between 3.8 and 4.9 hours. I said the average here was 4.5-ish, which is in this middle stack, or 5.4-ish. So underestimating could be a problem in this case. Overestimating, that's a safe thing to do. What if this was a different scenario? Like, let me see some other scenarios I was thinking about. Oh, we have, in addition to this COVID-19 epidemic, we have an epidemic of people addicted to opioid-type drugs, and the number of deaths related to opioid drugs has been climbing for years, and we still don't have a handle on it. So suppose some researcher develops a painkiller that is supposed to be not addictive, and we want to estimate the time that it kills pain for. So let's say we're talking about a pain killer, and we want to know what is the mean effectiveness time of the painkiller. And let's suppose that we have a bunch of data that ranges between like 5 to 15 hours from a sample. And let's suppose that this is not a huge sample. Maybe we have n equals like 30 people in the sample. And you got to think about, how many people you have and the cost of doing this, right? So we have to get these people in some kind of setting where we can monitor their pain levels somehow, which is a hard thing to do. And that's costly, right? It costs nurses, doctors, and so on. So maybe it costs like $1,000 per person to test this painkiller on them. So 30 would be like $30,000 in cost to test this. And let's say the mean of this particular sample was 10 hours, n hours. And then we made a confidence interval in stat key, and let's suppose the confidence interval ended up being from 9 to 11 hours for the confidence interval. And so the company then says, okay, we're going to say they're going to claim that the mean time mu is 8 hours. Okay, first, is 8 hours possible? Sure, it's totally possible. There were people in my sample that had 8 hours. Is it in my confidence interval? And let's suppose I had a 95% confidence level. Okay, well, no, it's not in there. So is it likely? The answer is no, it's not likely that that's the population mean. Sure, an individual, many individuals might have only felt the painkiller's effect for about 8 hours, right? They had very little pain for 8 hours. But as far as the average of 30 people, we're going to find almost no groups of 30 people with an average of 8 hours, right? Less, if it's a 95% confidence level, what we're saying is that if we repeatedly sample 30 people, the average of many, many samples of 30 people is 10. And 95% of all of those samples of size 30 are somewhere between 9 and 11. That means only 2.5% of samples were less than 9. And look where 8 is. So there's 10, there's 9. 8's way out here. Okay, so that's probably going to be the samples that end up in this range right here, less than 8, is probably going to have a probability of less than 0.1% is my guess. Okay, so it's possible that this claim is true, but it's very unlikely based on the sampling distribution. What do I tell the company? Well, I would say you should say the actual effectiveness time on average is somewhere between 9 and 11 hours, right? That's what the data shows. And we're 95% confident of that. And they say, well, we want to underestimate. Okay, why would you underestimate, company? Well, we want them to buy more. Oh shit, is that a good reason? On the books it might be, but what are the downsides of estimating low? Then a person takes more pills more often, which could lead to an overdose, even if they're not going to be addicted to it. So I would say it's dangerous to underestimate too much, because then people are going to take it more often, and that could be a problem. Every drug has side effects, right? If you take more of it, you increase the chance of side effects, or the severity of them. What about overestimating? What if they wanted to say the mean effectiveness time was 12 hours? That's not in my confidence interval. What's the problem with that? They might experience more pain because it wore off in around 9 to 10 hours, and then they wait till 12 hours later. Okay, so pain can be a problem. It can be debilitating. It can keep you from focusing. Okay, so there's a problem in overestimating too. I think underestimating in this case is more dangerous, because I'd worry about increased side effects and overdosing. So again, every situation is different. We have to kind of balance what to do. Is the actual mean time 10 hours? The answer is, I don't know. Is there a 95% chance that it's 10 hours? The answer is no. That's not what the confidence level means. All the confidence level means is that 95% of similar samples had an average of around 10 hours. Actually, no, that's a lie. That's not what it means. Let me write down what it means so I get it right. So this is interpreting the confidence level. Thank you for telling me what the mean was back there. I gotta figure out how to get alerted when there's chats. It's annoying that I can't see that. So interpretation, and this is on the critical thinking. I can't spell. As usual, interpretation, there we go, hooked on phonics, of a confidence level, not a confidence interval, the confidence level. And this is a weird thing, confidence level. And I mentioned in other office hours what it is not. I'm just going to state what it is here. For example, 95%. It's confidence in the process. What process? Of collecting the data and then from that data, building a confidence interval. Meaning 95% of similar, and I can show you a graphic of this in a sec, similar samples. Did you ever notice that a B and a P look very much alike? They're just flipped. 95% of similar samples of the same size will contain actual population value Does that mean my sample is one of them? No. Does that mean there's a 95% chance mine is one of them? And the answer is not exactly. This is what it means right there. Right? It's not really the probability of success though, which is kind of odd. A graphic of that StatKey can make for me. If I go to there, let's see, where is that? Sampling distributions for mean. And then let's try countries with internet. So they have 203 countries. That's the number of countries in the world at the time this was taken. So this is a population, not a sample. From this, I'm going to choose samples of size, let's go with 25. Okay, so if I create one sample, it's going to grab randomly 25 of these countries. Some of them may be picked more than once because they're all put back in the hat after we look at them. And I'm just going to do this thousands of times. Actually, I only wanted to do it 100 times. Let's reset and do 100. Okay, so some of these countries, when I resample, sometimes I hit the actual mean, which is about 43. Here I'm at about 43. And then if I look at the confidence intervals generated, so every one of these green and red bars here is one of these samples I took over here of 25 countries from the 203. And the green means that the 95% confidence interval generated from these samples here, the green means we hit the real mean. And this time we know the real mean because we have the population data. We usually don't. But every once in a while, 1, 2, 3, 4 times, 4 out of 100 times I missed, okay? Now, this was a simulation, right? And it's like rolling the dice. Every time is different. If I roll a dice 60 times, am I going to get exactly 10 ones? The answer is no. So here I got 96% of the time, my interval captured the real mean. But you never know whether it does or not. Okay? So if I reset and generate another 100, same thing happened. I got about 96% of my intervals caught the real mean. So this is kind of an illustration of what confidence intervals are trying to do. We have this black bar, which represents the population parameter we're trying to find, which we never truly know. And if it's a 95% confidence interval, that means most of confidence intervals that we make out of good representative random samples actually contain the real mean, but some of them don't. Could mine be one of these red ones? Yep, could be. I don't know. So the real population mean could be above or below the interval I stated. I don't know. That's life. Okay, that is a lot of detail related to application 6. Your job on that one, there's my course page. That's not it. Over here, And the video I just made on this, I will link here. I'm going to stop at this point.